So let's have a brief discussion on modeling concept for simple shear building models. Okay, so this is a shear building model. Uh, the reason why they're called shear building is because the behavior is mainly influenced by lateral shear, brought about by lateral forces. Okay, so these are lateral shear, which acts horizontally, such that your beams here are assumed to be rigid beams. Okay, they do not flex at all, and that for that reason, the behavior of such columns which are flexible, uh, assumes this type of deflection. Okay, okay, so this is now your lateral drift or displacement. Assuming this is rigid beams. Okay, these beams here are rigid, and these columns here are flexible. That's why when a member is flexible, it is given by the inverse of flexibility. Normally, the property is a K value. So the equivalent system for the shear building model is actually the mass spring model. Okay, so this is a mass spring. Sometimes there is a damper or a dash button. So this is a shear building. So these two model are equivalent. The only difference is this is a mathematical model or an analytical model wherein you can take the free body diagram to analyze the forces, simpler than the prototype building model. Okay, now I'd like you to take note that about the pattern in which your stiffness is assembled. So we have to assemble the stiffness in a manner so we can actually use the data for dynamic analysis. Okay, I'd like to take note also that the mass is lump, okay, or is concentrated to one point only. So this is a lump mass. So it is, for simplicity of computation, it is very common that you assume the mass to be lump at a certain point. Okay, and this degree of freedom here constitute uh, your let's say y1 coordinate and y2 coordinate there. It's equivalent to a y1 coordinate here and a y2 coordinate here. Okay, Okay, now how do we assemble the matrix without doing the free body diagram? So the technique of what you call connectivity. So let's just look into because this is very simple. The connectivities are easy to determine. So connectivities has something to do uh, on how the masses are connected because these masses dictates, okay, the number of mass is equivalent to the number of degrees of freedom normally for shear building model. Not for special cases, of course. In every rule there is an exception, okay. But for this you will take note that mass 1 and mass 2 simply defines a 2 degree of freedom system. And in order for us to assemble now the capital K or the structure stiffness matrix K, we can uh, say that we have to allot a 2 by 2 matrix or array to accommodate the individual stiffnesses of the column elements uh, in a pattern that which we can easily modify from one case to the other, okay. So these are now the capital K's at 1 1 1 2 2 1 and 2 2. If you will look on the relationship of the rows and the columns in the matrix. Now each element here K1 defines a value of your flexibility or stiffness. So for an element, let's say K of an element, in a simple shear building model, this is equivalent actually to a 2 by 2 matrix, very similar to a truss system. But of course, it's not an AE over L, but it's a negative K1, sorry, it's a positive K1 of the element, or simply K. This is a this is a matrix K of the element. You have now your K11, okay, K12, K21, and K22, okay. Or in all of these values for a certain element, let's say K of element 1, are simply the same. They simply signify one value, which is K1, K1, negative K1, negative K1, okay? Because this is, again, as I've said, similar to a bar element. Which simply accommodates compression and tension forces actually, okay? So how do we now assemble, of course, for K2 of element 2, this is simply a K2, negative K2, negative K2, K2, okay? So this is how the stiffness of a bar element uh, is actually distributed on the actual, okay, as far as the actual forces are concerned. So you have a, a locally 2 degree of freedom in a bar element. So how do we assemble now the K values? So let's go back into the connectivities of your structure stiffness K within the system. So how do we look into the connectivity? Okay, so we consider now this structure stiffness matrix as defining the global stiffnesses of each coordinate. Mainly here, it's defined by the coordinate 1 and 2, y1, y2, and y1, y2. Okay, so it's a row column order. Okay, and we just look into the figure. We will be confused if we look here, but if you have some experience, you can also omit the analytical model and go directly to your shear building model. So, but if we take a look here, it's simpler, no? That the connectivity of the y1 coordinate is defined on the basis of two springs. They are connected by two springs here, K1 and K2. Okay, so you read this as for your structure stiffness K connected on the coordinate system 1, and you call that now your K1, 1. Okay, so the connectivity is 1 and 1. So this is now your K 1 and 1. You will simply uh, put all connections of the spring as identified on the model itself. So the connectivity of your coordinate 1, or simply your mass 1, if you like to term it as your mass 1, is actually the sum of this individual stiffness of K1 and K2, because these are connected. So it's additive always. Okay, so this becomes K1 plus K2 in 1, 1. In 1, 2, okay, in 1, 2 connectivity, you will notice that, okay, this is now your coordinate 1, 2, row 1, column 2. The connection, okay, between 1 and 2 is only defined by one spring, and that is K2. And don't forget the negative sign there, because if you will derive the stiffness of a bar element, you will notice that the simple for a bar element, it's okay, it's a simple 1, negative 1, negative 1, 1, AE over L. Okay, but this is for bar element, no? So we're not going to use this. But it's a positive, negative, negative, positive. So similar with this, it's a positive, negative, negative, and then connectivity of 2, 2, you only have K2 there. So that's how to do it without really doing a lot of free body diagram, especially for common models like this one. Now, for a little bit complicated model like this one, we have another spring attached to to the mass M2, which influences your coordinate Y2. Okay, so you have a coordinate Y2 here and Y1 here. Still, this is a 2-degree of freedom system, because I want you to take note that you simply count the mass and it will give you an idea. It's not all the time correct, but this is the easiest way to do it for very basic situations like this. Okay, so 2DOF. So you have now the equivalent shear building model here, which states that another column might be attached. Okay, you can do it differently, but this is one way of interpreting this analytical model. Another column K with K3 stiffness is attached to the mass M2. Okay, so that is the attachment. Okay, and how do you define now your structure stiffness K on the basis of connectivity alone? So we simply again do ocular observation on Y1. So this is a 1, 1. Connected is K1 and K2. And for 1, 2, okay, so this is now 1, 2. Connected is K2. It's negative. Okay, remember this is the number of the column number is 1, 2 there, and the row number is 1, 2 here. Okay, so this 1, 1, 1, 2. Okay, and then 2, 1, it's a negative K2 also, K2 and 1. And then a 2, 2 here will involve now a positive K2 plus an additional connection K3 there. So this is how to do it. Okay, so easy as looking into the connections without any free body diagram involved. Of course, if I ask you to do it using the free body diagram, you don't have a choice. And for the last, a more complicated one, we add one story. It's not complicated actually, but similarly, we have a 3-degree of freedom system. You count the mass 1, 2, 3, and then you assemble it right away. By the way, this may be interpreted in a manner shown in the shear building model. Okay, you have a K4 attached to M2. Okay, with a certain stiffness, and this is K1, K2. I forgot to place K3 here. Okay, so this K3s. Okay, so how do you now apply the connectivity? Again, you write the coordinate system involved. You have a 3DOF, and then take a look into the model itself for connections. Okay, a K1 1 simply is a K1 plus K2 there, and a K1 2 is 1 and 2 is connected with a negative K2 there. Okay, always negative when it jumps from one coordinate to the other. A K21 will be the same because this must be symmetric. And then a K13, so look at the jump 1 to 3, they are not connected at all. Mass 3 is not connected directly to mass 1. So there is only a zero value here. And also 3 and 1 are not connected. So for K22, you have a connection between K2, K3, and K4. So this is where K4 will come into the picture. Okay, so K2 plus K3 plus K4 for 2, 2, 1, 2, 3. And for 2, 2, 3, so 2, 3, you have a negative K3. For 3,2, you also have a negative K3. And for 3,3, you have a positive K3. So this defines now your structure stiffness to be used on the analysis. Okay, so I hope I have given you some enlightenment on how to assemble the structure stiffness matrix K without doing free body diagrams using the principle of connectivities. Thank you.